Oh, actually. Okay, there we go. It's working. Shaking is crazy, huh? Okay. So, let's see. Actually, you know what? I want to show the energy diagrams for all of these. Let's take that back. I want to show the energy diagrams for all of these together. So that's what I'm going to do. I'm going to make a blank slide. And we'll talk about the first step in the attack. Right? So this is the first step in the attack. And I'm going to take the ortho one first. So in the first step, what do? You make a carbocation, right? So carbocation energy formation is going to be large. So we'll go like this. Well, actually, you know what? I don't have to move this whole thing down. So this is energy this way. This is for ortho, so I'm going to put an O on top of it. Okay. And then it goes to a carbocation intermediate. And this is all relative. It looks like a duck. This is all relative. What I've just done, right, is I've formed this carbocation, which has this sigma complex. What's the next thing that happens after this? Hydrogen gets pulled off, and you form the aromatic ring again, right? So do you think that's going to be hard, or you think that's going to be easy? And you have to give me a why. Easy. Why easy? Yes, you're forming an aromatic ring, so it's going to be really stable. So then you know the next part of this is going to have a low activation energy. And then you're going to go to the product. Let's assume the product's a little lower in energy. It doesn't really matter. But that's for the ortho attack, right? So now we're going to go back and look at the meta attack. So in the meta attack, right, you notice in the ortho attack you have the extra resonance structure here. Right? Here you don't have the extra resonance structure. So what does that mean about the energy of that intermediate? It's going to be high, right? So if you go back to the diagram, right, to do the meta, it's going to go like this. It's going to form an intermediate. Again, the next activation energy hump is low, right? So it's going to come down like this. So this is for meta. So that's a horrible diagram, but I drew that with my finger, so what do you expect? Going back to para. If it works. If I don't like it, can I badmouth it?
Sure.
Awesome. Wow, it's all fancy. Okay, so if you look at this one, again, this has the additional, right, resonance structure because the chlorine can donate electrons. The next step is removing of the proton to get back to the aromaticity. Now, if this isn't any better, I'm going to have to eat some words here. So what's the activation energy going to be like? Is it going to be the same as ortho? Should be lower because sterics aren't involved anymore, even though the groups are small. So para is going to be down like here. Probably the same intermediate stability. Probably the same product stability going down like this. So down here I have meta. Down here I have ortho and para. Or sorry, they're all probably at the same energy. Because they all have basically the same substituents on a benzene ring. So there's para, less sterics. Which one are you going to get more of? Don't know yet. right? You never did the experiment. It's probably going to be ortho because the groups are small, right? So even though para has a lower energy, ortho, because there's two ortho positions, you may end up with more product. All right. That's all of that. I'm just going to review through this is a nice slide, like strong activators, what makes them strong. So we'll review really quick. What makes these all strong activators? Lone pair of electrons next to the ring. Why is nitrogen a stronger activator than oxygen? Lower electronegativity, right? What about O minus versus OH? Which ones do you think are more strongly activated? O minus, because more electron density, doesn't have the hydrogen, better electron donor. In general, I don't know where this one falls with the rest of them, but this is in order of increasing strength. This is the strongest activator. This is the weakest of the strongest activator, right?
Wait, why was O minus stronger than OH?
Oh, because it has negative charge. Negative charge is more electron density to localize in the ring, right? And it's an electrophilic reaction. So when the electrophile comes along, when it attacks the ring, it'll attack the ring with a little more vigor, unless it attaches to the oxygen, and then you're kind of screwed. But beside the point.
Comparing the OH to an ester, no, not ester, ether, OR, right?
Yeah.
Would the OR beat the OH? Because doesn't the R...
Yeah, so the OR would probably fit in between these two here. Because it has an R group that donates electron density, same way that this is a better activator than this is a stronger activator. Having said that, those R groups, right, don't make that big of a difference. It's just better. What really determines what R groups go on there is what you want on there. Just to know, though, that when you add them, it'll be more reactive than without it. Okay, so what makes all of these moderate? Oh, you know what? Maybe I'm wrong on that. I just saw this one. This is the one you're talking about, huh? I don't know. Well, this is the strongest of the moderate activators, but yeah, I'll have to think about that.
Is that the whole deal about how the carbonyl group can the oxygen can get the double or can get a pair of the electrons, so then the lone pair on the nitrogen donates over to...
Yeah, so ignore this guy for now, but what this one here, right? This is an activating substituent. These lone pairs, you know those are activators, but they have this carbonyl group next to them. So the carbonyl group causes the electrons to share, right, in resonance from either go this way or go this way. And by splitting up which way the electrons go, you decrease the amount of electron density that gets contributed to the ring. I'm going to look up that OR group. I have to understand that better. I have an idea, but I don't want to say it. Okay, go ahead.
Question about the benzene ring. Is the benzene ring, does it like to donate electron density, or is it more towards...
It donates electron density.
Okay, so
Like a phenyl group would be an activating substituent.
Cool.
Okay, weak activators are all alkyl, right? Weak deactivators, and these are weak, alkyls are weak activating substituents because they don't have a lone pair to contribute, so it's all through hyperconjugation. Right? Weak deactivators makes them weak, right? They withdraw electrons by electronegativity and then donate very weakly back by resonance, okay? Questions?
You mentioned that if you have a deactivator on the other side of the deactivator, that makes the deactivator stronger.
Yeah.
So
like these guys here. So you have a deactivating substituent here, pulling more electron density out of this carbon, making it electron deficient. Well, if I put this group, right, next to this, then it's also pulling electron density out very strongly because of its charge, basically dipole.
So then in that case, from 2 or 3 slides back, you had an activating group next to an activating group.
Wait, hang on.
What? Yeah. The moderate activators. So does that slow down?
Yeah, so this is an activating, this is deactivating. This is electron donating, this is electron withdrawing. So by putting this group here, makes them less activating. That's why they're all moderate, where all these are strongly activating. Okay.
For the halogens, even though they're deactivators, the weak deactivators, you treat them as activators when it comes to.
We treat them as orthopair directors. Yeah, because of the lone pair. Yeah, so that's where people get confused. It's they think, well, chlorine's deactivating, and then they always want to say meta-directing, but because of the lone pair, and adding the resonance structure makes them orthopair directors. All right. Okay, so multiple substituents. Have I talked about this one at all yet?
No.
Okay. What's the orientation of the two groups on the ring? Pair. So you're going to be asked to synthesize this. Somebody says, propose a stepwise synthesis. That means propose the reagents and all the products that you make in between. Propose a stepwise synthesis for this. All right, ignore this. For this, okay? I did talk about that part. I didn't talk about this slide yet. I just realized. That's the product from the previous slide. You always look to say, oh, in order, so ignore this. How would you make this, right? How would you make it? What's the, say very clearly, what has to be on the ring first? What's that? The methyl group, because it's activating, but it's orthopair directing. And so you look at the orientation on the ring, right? And you say, oh, activating substituent makes it para, so this has to be first because the product is para. So you do alkylation first, followed by nitration, and they'll be in the para position. Okay, now here, you're going to brominate this. So this is your product, right? You just went through the process of making this. What's the product of this going to be? And how do you know? It says somebody do this. That's right, it's this. It's this one here. Why is it here? Because this position is meta to this group, which is a meta director, and orthopara to this group, which is an orthopara director. So you can control where this substituent goes, right? Or know where this substituent goes based on what the two functional groups are. So if you're asked to determine the position of a third group, you look at the two existing groups and you see how they either work against each other or with each other. In this case, we'll get to that. So now you have this, right? They're both orthopair directors, but this position is ortho to the OH, and this position is ortho to the CH3. So the stronger activating substituent will determine where the product goes. Okay? So you end up getting that. So another one. Okay. Now, if you have two substituents that are essentially the same, all right, this group is a lot bigger, right? So one group is a lot bigger. These are both orthopair directing. Then you have to consider, well, which one of those will form better? Yeah, this will be your major product here. Okay, major. This is your minor. Here's another. So there's your major product, there's your minor. Here's another one. Oh yeah, why isn't, sorry. So if these are meta to each other, right? When you run this reaction, this is ortho to both of them, right? This is ortho, this one pair to this one. This is meta to both, so you don't expect anything there. And this is ortho to this one, pair to that one, right? So the result is, right, major products this one, minor products this one, and because of sterics, you don't actually see this one.
Now, what if you would have two methyl?
What if you had two methyl groups? You almost never see, okay, you're talking about, hang on. Okay, hang on. Answer your own question. That's your starting material, right? Where is the product going to form?
Because you're the one steric. We said it would be.
Yeah, well, this one's bigger, right? But this one's not bigger.
So would it be right in the middle?
So it could be here. It could be here. But again, sterics say this position is so sterically hindered, it's not going to be there, even though it's ortho to both. It would rather be ortho and pair to one than be ortho to two. And you almost never see the substituent go in the middle unless you happen to be able to force it to go in the middle. Okay? By blocking all the other available positions. So if you put what they call blocking groups in there, then it's possible, even though the reaction's slower, it's possible to get a substituent on this position. But without using blocking groups, just running this reaction, okay, you don't get that. Do you want to know what a blocking group is?
Yes.
Okay. If this is the position you want, this is the desired position, what do you have to keep from happening? And let me do this. I'm going to number this. 1, 2, 3, 4, 5, 6. What do you have to keep from happening? Keep the reaction from attacking 3 and 5. So you guys remember protecting groups, right? Hopefully remember protecting groups. A protecting group is something you place on another functional group to keep it from reacting. In this case, the protecting group is usually sulfonation. So what you do is you run sulfonation. That's fuming H2SO4. And then what you end up with is you're going to be able to produce like that. Because what you're going to do is, since positions 3 and 4 are reactive, right? You add the first sulfonate group. Sulfonate is a meta-director, right? And so the first sulfonate group, let's say it's this one, this is meta to this position. This is also meta to this position, but because this one is in between two substituents, it's much slower. So concentrated sulfuric acid, you get the 2 sulfonate groups on there, you get the 2 methyl groups on there. And then if you do a quick analysis of the structure, right? Meta-directing, that points to here. Meta-directing, that points to here. Right? What is this? Ortho-para-directing points to here. Ortho-para-directing points to here. So everything points to that one position. So then what you do is you do your nitration. Or whatever the reaction is. And then you can add the one group at the top. Well, that's a good question, right? I'm going to put, I don't know what I'll put up there. It looks really cool, though. I'll do NO2. This is SO3H. I don't know if you remember when I talked about sulfonation reactions, one of the cool things about sulfonation reactions is they're reversible. So if you do it in concentrated sulfuric acid, it's a Le Chatelier's principle thing. Benzene. Con H2SO4. Sorry, internet's really slow right now, or my network's really slow. That gives me a sulfonate group. All right. Le Chatelier's principle, dilute H2SO4. And it goes that way. Okay? So you can sulfonate, block a position, and then desulfonate. So that's the principle you'd be using here. Let me do this real quick. Yeah, like that. That was tricky, huh? All right. First thing you do is you sulfonate, then you nitrate, and then you can desulfonate it. I'm trying to get this pen to keep up. It's not the pen, though. The pen's great. It's my internet that's really slow. And then you end up with this really cool looking molecule that looks like it has a head on it and two arms. Yes. Hang on. What did I do with that? So you want to put something here.
I don't know, is it possible?
Yes, it is. But it's not simple. Yeah. I'm just trying to, yeah, it's not simple. I have to think about it. There's a way to do it, but I can think of a way, and it's like many, many steps that we haven't covered some of the reactions yet. We will later, but right now it's many, many steps. I'm not sure there might be a simple way to do it. Oh, well, if you want it to be meta, here's the simple answer, okay? Put a meta director here first, and then add the other two groups. That's like the simple answer. Right. Yeah. But it's not quite that simple either. But I'll look at it some more after class. Yeah, so actually the book has a whole set of slides on blocking groups. Let's say you wanted to put the bromine next to a large T-butyl group. Why can't you put the bromine next to a large T-butyl group? Because it's a large T-butyl group. Steric effects, forced to be para. Okay? So in order to keep it from being in the para position, you add a blocking group, you do the bromination, and then you remove the blocking group. So it's a pretty standard procedure. Okay? Sulfonation, this is the slide that I was drawing earlier. Right? Sulfonation occurs as a reversible process. Concentrated sulfuric acid pushes the equilibrium to the right. Dilute sulfuric acid, it goes to the left. So in order to put something ortho to this larger group, the first thing that you do is you attach something in the para position that you can remove Second thing you do is you add that functional group, and the third thing you do is you remove that that blocking group that you added, the sulfonate, okay? Same principle as the one that we did earlier, but this one's actually like a lot easier to understand, but sorry about that. It was the question that got asked, so I figured I'd go with it. All right. Oh yeah, nice slide. Synthetic strategies. Right, so these are all the things that you can do. This is a great place to start your reaction notebooks for your exam. That's next Monday.
Exam next Monday.
Yes.
Oh, sorry.
Wait, what did he say?
He says the exam's next Monday. That was your question. We're going to move on. No, we are. No, what was it?
Oh, so in order to add a bromo group to that spot, we have to use sulfonation. But is there like a limit on how big of a group we could possibly add to the meta position?
Probably. I don't know what it is. Yeah. Okay. Here's a couple of other things, okay? They say, how might you make 3-nitrobromo-benzene? Okay, so or how might you make, let's do 3-chloroaniline. 3-chloroaniline, right? 3-nitrobromo-benzene we've already done, actually. 3-chloroaniline is this. How might you do something like that? If you put the chlorine on first, right? Chlorine's an orthopair director. So then the nitrogen, however you install it, can't be in that position. The amine is a orthopair director. So if you put that in first, right, you can't put the chlorine paired to that. And a blocking group doesn't help either because both of those are orthopair directors, so they're both one directed the orthopair direction. So you can't do it like that. You have to add an extra step. And the extra step is to recognize some functional groups can be changed from orthopair directing to meta directing, and some can be meta directors switch to orthopair directing. The really common ones are on the next slide, so I just want to walk you through these things, okay? So nitro groups can be reduced fairly easily. This is very similar to the Clemenson reduction, just no mercury amalgam. You take the meta-directing nitro group, you reduce it with hydrogen from the HCl, and you produce an orthopair director. Okay? So in that previous slide, what they probably would have been done is you probably would have nitrated the ring first, added the chlorine, and then reduced the nitro group. That is, you would have taken this product first, added the chlorine to it, and then done that same reduction that's shown here to produce an NH2 out of the nitro group. Okay? So that's like the simple way to do that reaction. Alkyl groups are orthopair directing, right? So this is the metas turning orthopair. These are the orthopairs turned to meta, right? Alkyl groups are orthopair directing, but you can oxidize them with permanganate or Jones reagent, right? Convert them into carboxylic acids, and these can be meta directors. Okay. If you want to go back that way, you can do it. It's a little bit more complicated. We haven't covered the reactions yet. But basically, you form an acyl halide out of it, and then once you have the acyl halide, you can reduce it back to the methyl group. Okay? How do you make this into a halogen, by the way? You guys know this reaction. How do you do that? You guys remember? Thionyl chloride? It's basically treated as an alcohol functional group. Thionyl chloride will produce a Cl, and then there's a specific reducing reagent for taking acyl halides and converting them into alkyl groups. It's called Roseman's reagent, but it's basically a catalytic hydrogenation. Okay. We haven't covered those yet. You could take this, right? This is acyl group. That's meta-directing, and you can convert it into an ortho-para-directing group. Okay. This, this is Clemenson's reduction. But you notice these two look really similar, and the only thing different is the presence of the mercury. And then finally, right, ortho-para-directing. This is a deactivating meta-director, right? NBS, you just brominate this position and produce this tribromide, and that's a good meta-director, okay? All right. Some limitations of electrophilic aromatic substitutions. Nitration conditions generally cause amine oxidation leading to a mixture of undesired products. There's a couple of things that happen, okay? In addition to this being oxidized and you're getting like NO and NO2 out of it, okay? When you protonate this, it strongly deactivates the ring, okay? And under nitration conditions, right, amines turn into meta-directors, and you don't get this as the product. Plus, you convert the amine into like NO2s and NOs. Another limitation, right? Friedel-Crafts reactions, right? They're too, they say slow, but too weak, right? To work, these are too weak of an electrophile to work with strongly deactivated groups or moderately deactivated groups. So while if this was a halogen, Friedel-Crafts would work, right? This moderate deactivator keeps this reaction from happening. So anything moderate or strong, you can't do a Friedel-Crafts reaction on. And the third, oh, there's one more that I thought of the other day. All right, well, we'll go with that for now. All right, design synthesis for this. How would you make that? What? How do you make that? Starting with benzene. Say that again. Speak loud and proud. We're going to start with benzene. Oops. Sorry. It's jumping around on me. Ah, there we go. Start with benzene. Okay, I'm just going to show you because this is one of those tricks. Okay? But you should recognize that. How do you make a carboxylic acid next to a benzene ring? Oxidation of an alkyl group, right? So if you have a carbon with a hydrogen on it next to the benzene ring, either an aldehyde or CH2 group or CH3, that can be oxidized to carboxylic acid. So you're starting with benzene. The fastest way to get to that product is, you might think, alkylation, right? If you did the first alkylation, it would come out here or here. You get one anyways. What would the second one do, though? It would be para. So you can't just use, like, this and AlCl3, because what will end up most likely happening is you'll end up with polyalkylation, but you'll probably get that. Right? And then when you oxidize it, those carboxylic acid groups would be para to each other. So the way you keep this from happening is you limit, right, where the second one goes by attaching it with a chain to this one. So if you take that, and instead you make that, right, the first alkylation will do this. Now that you have this chain on the ring, it can't reach all the way to this position. And so what ends up happening is it attaches itself here. So you're using the limitation of the chain length to force it to be in the ortho position and rather than attaching in the pair position. Okay? You can do it with a 3-carbon chain too and make a 5-membered ring as well. So that's the first step. Second step, I don't know that you actually isolate that first one. The second step would give you this. And you notice the reason I added 4 carbons here, that's a 4-carbon chain. It's going to be a 3-carbon chain too to make a 5-membered ring. Okay, is because 2 of the carbons in this 6-membered ring are a part of the original benzene. And the 6-membered ring is relatively stable, so you figure that'll be a good one to make. Turns out kinetically, 5-membered rings often form faster than 6-membered rings. But okay, so anyways, so you get that, and then last step. Jones reagent. You just have to know it. Yeah. So that one of the tricks, anyways, for installing these functional groups side by side is just to limit how far the second one adds by putting it on a chain. Okay. A carbon chain, I mean, not a chain. Okay. Right. So we did 2 functional groups and figured out how to make a 2-functional group molecule. Now we have to do a 3-functional group molecule. Okay. So we have 3 functional groups on a benzene ring, and you want to design the synthesis starting from benzene. This will happen to you a lot. I'm going to give you benzene, say starting with benzene, make this, and you have to outline the intermediates and the reagents, okay? So how do you determine which group gets added when?
So do you mean like during the reaction?
Yeah, during the sequence of reactions, how do you determine which functional group gets added in which order? Okay. The easiest way to do it is start with the product and remove one and say, if I added this, where would it get added? Okay. So in this case, for example, if you said, oh, here's a bromine, right? Could I have added that one last? The answer is, well, it's ortho to this one and pair to that one, so no, because those are both meta-directors, all right? Could it have been the nitro group as last? So this is an ortho pair director. So we're going backwards. We want to draw the product that was right before that one, right? So if you remove this one, right, this is an ortho pair director. This is a meta director. So this is a good position for this to be in. You still have to go through the trouble, though, of saying, could this have been the last one added, right? And you're going to have to work that branch out. That one has some problems with it. But this one is meta to this and pair to that, right? So it is possible that you could have added this one last, except, right, how do you put that on there? What's the reaction? No. How do you get this group on there? What kind of reaction do you use to put an acyl group on? It's a Friedel-Crafts reaction, right? What is this? It's a deactivating substituent. So Friedel-Crafts reactions won't happen on strongly deactivated rings. So even though either one of these could have been technically added last just by doing ortho-pair directing, practically this one can't be added last because you have 2 deactivating substituents on the ring. Okay? So that's just not going to happen. So the molecule before this one, and again, this is that retrosynthetic arrow, right? Has to have been this one. And now you're down to a problem that you've solved before, because now you have two substituents. You just have to figure out which was the last one to be added. Right? Well, acyl groups are what? Meta-directing. And halogens are orthopara-directing. And since the substituents are in the pattern, then the acyl group had to have been added the step before this. So the reactant before this one is this one. So starting from benzene, first thing that you would do is you would do a halogenation reaction. That's just Br2 and iron, right? Ferric bromide. Once you have the halogen installed, you can do the acylation reaction because that is the most deactivating substituent you can have and still do an acylation reaction. And those are the weakest deactivating. So basically everything else doesn't work. And then once you have that, then you do the nitration, and you'll end up with this product, okay? So multiple substituents, all you need to do is look at the substituents that exist and say, if I pluck this one off, can I add it back to that position? If I pluck the next one off, can I add it back to that position? Go look at all three of them, and then you have to analyze them for, is this something I can do? And then you have two substituents at that point, and then you just go through the process. Well, what's the orientation of the two substituents? They're either orthopara or they're meta. Right? And then you have to decide which group gets added last, if there's a preference for which group gets added last. And they walk through the whole process here. Now this is actually how you do it part. Right? So you do bromination, you do a Friedel-Crafts acylation, then you do the nitration, and then you're done. Okay? So when they say, or when I say, draw a stepwise synthesis, this is the stepwise synthesis for that product. Right, every product that goes in between and all the reagents. Well, I have 4 minutes, so what I'm going to do is stop and